In the age of big data processing, ubiquitous computing, and the Internet of Things, industrial systems are equipped with an ever-increasing amount of software. It is clear that developing software for industrial systems is different from developing applications or apps. Just compare the form factors of magnetic resonance scanners with mobile phones, tablets, or notebooks. One major difference is that industrial systems must be much more robust than consumer devices. Another requirement that distinguishes industrial systems is that they often need to last for many decades, which does not allow us to always employ the most fashionable languages and libraries, but the most reliable and resilient ones. Development for consumer devices in 10 years will be totally different from today, and as we all know, most of the current high-tech phones will at that time be either deformed or combusted. Our proposed approach of McFSM, short for Multiple Coupled Finite State Machines, solves two important problems. It is based on very solid and reliable techniques for programming industrial systems, and it allows for a system global description of appliances. It also totally avoids the common problem of state space explosion that most traditional finite state machine approaches encounter. Being able to handle huge state spaces in a way that is easy to grasp and which can be simultaneously viewed in different ways, from textual to graphical, is another of the great strengths of this new approach. Let's consider an example that underlies many industrial scenarios, a coupling of sources that jointly determine the status of an output element. We use two switches, S1 and S2, and as output a light with three values, red, yellow, and green. Moving over an edge highlights the edge in all associated views and visualizes the global interrelations of the local components. Besides providing different clear views of the system as a whole, our user interface shows classes, nodes, edges, events, and so on in an hierarchical namespace. We have crafted a powerful pattern matching language which allows us to specify complex interrelations between components in a manner exponentially more concise than traditional approaches. Of course, we did not spend all our time on making the user interface look great, again, but made sure instead that the tool can generate working code from the DSL. A TCL backend is intended for rapid prototyping and interfacing generated code with existing industrial components. C and C++ backends allow the generated code to be used on actual industrial hardware, even without substantial runtime environments or operating systems. In the future, we will apply our approach to solve industrial problems from many domains and ensure that the language is intuitively usable. We are looking forward to sharing more details on this and also on the mathematical verification aspects behind McFSMs with you.